All right, let me pull up the practice problems.
I tried to watch a video too, and I don't know how to help.
Okay.
This concept is but it was a
Well, the good news is it's just nomenclature, right?
yeah.
We know nomenclature. There, we just have that weirdness with the two words versus the one word, right? So let's just get some practice. So first off, acid. So this one we should be good for, right? Because we have that's all of these acid derivatives. We start by naming it as acid, and then we add the weirdness to it. So we know that this is carbon 1. And 1, 2, 3, 4, 5, 6, or 4, 5, 6. And we might as well count the direction as the chlorine, right? So it's going to be it'd be hexane, except we dropped the E and put oic acid. So it's hexanoic acid. That has a chlorine on carbon 5. And has a propyl group on carbon 3. Okay, where do you want to go next?
Down.
Down? All right, what's our parent molecule?
Starting from
So 1, 2, 3, 4, 5, 6. So it'd be hexanoic again. Except it's what type of functional group?
the O's. We're gonna end in O8.
Oh, wait. So this is an ester. So we drop the acid and we name it like it's deprotonated.
And then I used cyano.
Yeah. So 1, 2, 3. So 3 cyano. Then we've got a methyl on carbon 5, right? So there's our parent molecule. That's everything left of the oxygen.
Yeah. We have an ethyl.
So we have an ethyl on the other side. So how do we indicate that?
Is it just a separate word?
Yeah.
Ethyl?
Ethyl.
Okay.
This is one that you're really not going to be able to convey verbally unless you specifically say space.
Yeah.
All right, we good so far?
Yeah.
Let's do C, and then I'll erase them so we can move everything up.
This one only does like an alcohol base. Because that's all it had.
We've got cyano.
Yeah.
I think technically an nitrile is higher on that chart, but you wouldn't get it wrong if you did that. So if we name it as an alcohol,
Yeah.
that's our parent group. We name it as 6 again. It is.
But I gave the alcohol was so I said like 5. Like how many left, right?
Yeah.
Oh, I got that one perfect.
The other way you could name this would be if you said 5-hydroxy. Actually, in the 5-hydroxy 2-methyl nitrile. 2-methyl. Yeah, I think it'd be 2-methyl nitrile. Because remember, for the nitrile, it's kind of the weirdness where you count that carbon. If you name it as nitrile, if you name it as a cyano, you don't count the carbon. But this is the simpler name, and this will get you the right answer. So this is what I would go with.
Okay.
But just in the interest, since we talked about these the other day. The 1-nitrile.
Right.
Again, I like this better.
Is it still NMI and then it doesn't have to watch?
Let me see what we're looking at.
It's the next one down.
It is an amide because it's next to a carbon.
Okay.
So this is the group that makes it an amide. So if it, yeah, so we name it as the acid, the 1, 2, 3, 4, 5. So pentanoic acid. And we might as well do we just have a bromine on carbon 4, right? 4 bromo. Except it's not pentanoic acid. We drop the oic acid and just say amide. Or bromopentanamide. You said pentanamide, nobody would blink twice. And then we just have those other two grains, an ethyl and a methyl, both on the nitrogen. So all one word. N methyl and ethyl or bromopentanamide.
That's right. It's like, it has two things.
And this is the one time when you do have to have because we're using the atomic symbol, right?
And then I saw factory.
When you went to check your answers, and
Yeah, well, I went to check the first one, and I was like, oh, darn it, I'll just do something like that.
that's really obnoxious. I did not realize that. I'm like, oh, it has the answers. I didn't actually click on any of them.
See, I was like, oh, I can do this, I'll check the answers, I'll figure out if I did it wrong, we'll retry it. Nope.
Yeah, some of these study guides, the ones you have to pay for, are worth it when they're focused on a specific test because I'm just teaching them material, right? But the test is going to have certain concepts it focuses on. These aren't always a scam. They can be really helpful when you're preparing for something specific and it's geared towards something specific. But I was just looking for practice problems.
Yeah.
All right.
No, E. Not
Oh, sorry. All right, so start by circling your parent molecule, right? There's our parent molecule.
Wait, okay, why is the rating?
Because when we have, just like with the aldehydes, when you have just a single carbon attached to the ring, we have a specific way of doing it. If it was 2 carbons attached to the ring, we don't name it as ethanoic acid, the complicated branch. The fact that it's just a single carbon attached to the ring, we're gonna just stick carboxylic acid on the end.
Okay.
So it's cyclohexane carboxylic acid. And then we just name the other stuff as a branch. So if we call this carbon 1 on the ring, that's where the carboxylic acid is attached. Got 2 methyl, 3, 4, 5 bromo.
I went the other way, but I got 3 bromo, 6 methyl, hexane.
So just in the interest of keeping the numbers
Yeah.
low, I would count that way because methyl and bromo are relatively the same priority. But again, you get the right answer either way as long as you're consistent. I'm not gonna mark you down on this one in particular.
Right.
Because the argument could be made that the bromine is slightly higher priority.
Okay.
That's a good question. Since we're in the business of focusing on spaces now. And then you also might notice that these examples, they're not paying any attention to stereochemistry. Technically, this one has 3 stereocenters. Right, all 3 of the carbons that have a branch on them would be their own stereocenter. So if it was specified, you could say R versus S for each of them. If it's not specified, treat it like we don't know what the stereochemistry is, like it's racemic mixture basically. We just kind of ignore it.
Right.
Excuse me while I build this in mole view real quick. It does not have a space. In fact, they actually put it has the space between carboxylic and acid. But they actually put the 1. I think that that's implied. So I don't think you need the 1. But either way, they wrote all of this as one word, except for that. If I delete the other things, yeah, all one word, cyclohexane carboxylic acid, which really feels like it needs a hyphen at least in there because it starts looking really cramped, but there's not. If you don't have the number there, mole view just slams all of this together as one word. I'm okay with that. Just know that that's non-standard. For this class, we've been using these hyphens this whole time. Technically, there wouldn't even be a hyphen here.
But that's ugly.
Exactly. Exactly. All right. So looking at these other examples, well, I is tricky.
Yeah, that's why I stopped. I was like, these look ugly. And if I can't find the answer.
So this is definitely where we break out that priority.
Yeah.
Since they're higher priority than ketones, and we have to go look up like the prefixes for a ketone and believe it's oxo, OXO.
Okay.
So you would just say 2-oxo, cyclohexane carboxylic acid. No. Let's see if there's any more that are worth. We haven't talked about, there's my cursor. We haven't talked about amines yet, so we're going to ignore that one. Amines are just when you have a nitrogen attached to a carbon that's not next to a carbonyl. So this is an amine right here. The prefix is just amino. So amino acid is literally a carboxylic acid that has an amine.
Okay. Is that what we're doing?
No.
But an amino acid
like in biology. In a biology,
be on the exam.
it will not be on the exam. I've got more examples that I did find from the book that I don't think we did yet. So I think we can just ignore the rest of these. We'll go back to the slides. Because we did not do any of these yet, right? We did that one and that one.
Oh, yeah.
But I don't think we did these. So let's do these ones.
No, these. Okay, we just. Okay, yeah, we did.
We did decided to write about solid acid structure on the board.
Maybe. And I don't think it says, when this all, right, if we just say, right. But it's, oh, right, it's. You know, there's an exam where I left say, well, something in a service that it's like, I'm stupid. I should have done what I would have.
That's a very common thing to do. The other really common one is they treat it like it's benzene,
Oh,
but how
yeah.
it doesn't have double bonds. And that happens a lot as well.
It's always the things that I like never forget that I always forget on exams. It's like even when I took my driver's test to get my license, turn signals were like the one thing that I never forgot. I was like, turn signals, I have that down. And it was like I did it wrong like 4 times. I like forgot about it because I was so focused on everything else that I like didn't already naturally have. And I was like, oh my gosh, are you kidding me?
Did you pass though?
I did.
I wasn't sure if that was an auto fail or
No. He was like, because I literally said it was turns, and I was like, oh my god. It's okay, keep driving. He's like, it's not a major one, like you're not gonna drive down for it. It's like, thank God. I forgot it like 4 times. It was so bad. And I kept saying it afterwards. I would do it and I'd be like, oh my god, I forgot again.
with the hyphen in it.
Okay, yes.
I wouldn't put the hyphen between cyclo and pentane.
No.
That probably wouldn't mark you down for it either. That just seems like overkill.
Okay. So it's. Yeah. Would we say with each? Fate? I don't know.
Close. You just dropped this bit.
Okay.
The C would be benzoic acid if it was the acid. So we name it that way first. Drop the ic acid, you would put YL chloride. So it'll be benzoyl chloride.
Okay.
Correct.
So, do, like,
Mm-hmm.
the parent molecule stops after the O that's in the carbons.
Correct. So if this was the acid, it'd be acetic acid or ethanoic acid.
Which one is I
think technically ethanoic acid. We drop the ic acid to turn into 8. Correct. 2 words. Ethyl ethanoate or ethyl acetate. Which you do know what that is. That's non-acetone finger polishing.
Oh, really?
Nail polishing, not
Yeah,
finger. Yeah. It smells, it's still a non-polar solvent, but it's not nearly as carcinogenic as acetone. One, two, three, four, five, 6. So hexanoic acid.
When it's drawn like the C of the short back, is it like double bonded O and then single O H?
Correct.
Drop.
It's still this structure, but this structure is really hard to convey in condensed form. So they just say CO2H. So the condensed form version of acetic acid is CH3CO2H.
Okay.
Right, we didn't learn what the structure was back in Gen Chem, but we saw that back in Gen Chem. We just collapsed it all, so it was even more condensed. Be C2H3O2H. Or actually, we would have put H in front. When we were back in Gen Chem and we were first learning acids. So that's why this is not a great way to do it. This works if you're an inorganic chemist, but if you're actually trying to show any of the structure, this is more common. And once you learn your keyboard shortcuts for subscripts, it's a lot faster to type out on paper than
That's true.
to get out a structure and draw it. Which is really where this all comes from. Back in the 1800s, when they had a printing press but no computers, they weren't taking the time to draw them out like this by hand. One, two, three, four, 5. So it's going to be, it would be pentanoic acid.
So we don't want to like completely drop.
We drop the end and change it to YL. and then put chloride.
Do we specify where the bromide?
It always has to be on the same carbon as the carbon
Okay.
before naming it this way. And then this one's also 6 carbons, except this is what an amide looks like when you draw it in that structure. So it would be hexanamide. And then the last one is practice with common names, but we don't want to mess with common names right now. I actually not. Yeah.
Two days?
So it'd be hexanoic acid. You drop oic acid and just get hexanamide. And actually, for the acid chlorides too, you do sometimes see them drop the O, just like for the amides. So we wrote it as pentanoyl chloride. You could write pentanyl chloride too, and people would know what you were saying. It's one of those things that you don't really think about, but you've seen it a bunch of different ways. I'm curious now what MolView does. It gives me the common name. Oh, so it does leave the O in for the systematic name, for the IUPAC name. The common name, I've never even seen this one before, so common stretching it was for this one,
Yeah.
for 5 carbons was so if you take that back to what the acid would be, it'd be valeric acid, which I've never heard before.
That would be.
I don't know. At break, I'll probably look it up because I'm curious where that came from too. All right, let's talk about reactions a little bit. This is another case where, similar to the aldehydes and ketone, pretty much everything is going to be some variation of one mechanism. And so we're going to talk about these all in relation to each other. And so then when we talk about how reactive they are, it's always going to be based on what the leaving group is. And so if it's the weakest base, that makes it the best leaving group, right? And so if we look at our different the leaving groups that are attached to the carbonyl, the chloride is the best leaving group, followed by the acid group, the acid anhydride, followed by the ester of the carboxylic acid, followed by the amide. The nitrogen is the worst leaving group of these. And the chloride is the best leaving group. And This figure has greater than symbol between esters and carboxylic acids, but they're really approximately the same. The reason we think of carboxylic acids being less reactive is we usually have more water around, which means if you have a whole bunch of water around and you have some esters, the esters will get converted into carboxylic acid, but that's more of an equilibrium thing than it is a reactivity thing. It's just because of the concentrations. And we'll talk about that in more detail. But what this also means is that anything to the left can be pretty easily converted to anything to the right. So an acid chloride we can turn into an acid anhydride, or an ester, or a carboxylic acid, or an amide, all pretty easy. Right, so remembering this order of reactivities is going to be really helpful for figuring out which side. All of these reactions are somewhat equilibrium reactions that are going to allow us to convert back and forth. But remembering which side is going to be favored is all going to be based on this. All right, so here's our basic mechanism.
So we need to know. We have to what is it?
Right, it comes back to, it's also related to what's better. Nucleophile, it's all based on this as well, right? It has to do with how stable it is once it's left. Chloride is the most stable on its own, and then goes down the line here.
Class next Thursday.
Depends, are you gonna help with senior day?
I'm supposed to help for as the master, and then we also have science. Your wife goes on. I hate both myself. I'm on the flight. Who's in the space? I was gonna let this table, but we had 2 people come by last time. Then the people be back. So I'm just gonna move the table out and we'll see what. We should have 4 of them. Oh, I think they take them for the cleaning thing.
Meta majors?
Yeah, well, they take you for not a class, then we take it.
Yeah.
See, figured out. Boom, done.
Yeah, we'll probably cancel class as long as everybody's helping out. I'm not going to cancel class so you can go skiing, but exactly. We're past that season anyway. There's no need. So next week will be review on Tuesday morning, test Tuesday afternoon, Thursday senior days for class. We're really coasting in for the final year. All right, so here's our basic mechanism. Basic is in the baseline that everything else is built from, not. Go ahead.
Not what?
Not basic as an alcohol.
So this is like a basic mechanism for all of the reactivity of acid derivatives.
So there's a lot of different combinations you can make out of those, but they're all going to come back to what we call nucleophilic acyl substitution. As opposed to our class 2 carbonates or aldehydes and ketones where we had nucleophilic addition. This is nucleophilic substitution instead. Right, and at its most simple, it's 2 steps. Nucleophile attacks, leaving group leaves.
Is C or leaving?
Yes.
What do you mean?
Anything from that previous page.
So like any leaving group.
Any.
Or any.
Sorry, for the acid chloride, the leaving group would just be chloride.
Yeah. Okay. Does it matter in this case the errors drawn from the lone pairs versus the numbers. It always matters.
No. I mean, it is most correct to show it to be a lone pair, coming back down to reform the pylons. But we all know that a negative charge is a lone pair at this point, so. Alright, so the only thing that's really, this is a pretty straightforward substitution. The only tricky bit is when your nucleophile attacks, you have to make room by breaking the pi bond. And then in the second step, when your leaving group leaves, you reform the pi bonds. So you basically temporarily break the pi bonds to make room for the nucleophile, and then your leaving group leaves.
You just gave us start and one finish. It's just C gets replaced with the file.
Exactly. So here's one example that matters a lot for biology. Is if you have an amine reacting with an acid group. It'll do that. Make an intermediate. It's called the tetrahedral intermediate. There's some proton transfer steps that have to happen. But the net result is going to be those get kicked off and you make an amide. Why is that relevant to biology? You know what that type of bond is called in biology? In biology, we call that a peptide bond. So they actually just misname their amide groups. It's an amide functional group, but in biochem, they call it a peptide. And a peptide is just what you get when you have an acid react with an amine to make an amide, and it goes through the same mechanism. It's catalyzed in the case of bio-living systems, but it doesn't need to be because equilibrium already favors making the amide. This is why peptide bonds are, we always talk about them as being really stable, right? Because it's pretty hard to take the amide. If I go back a slide, amide is the most stable of any of these. It's really hard to take an amide and go backward. And this is one too where, like I said, this reaction will happen when it's not catalyzed. When it's catalyzed, it happens quicker, but you have to pay an ATP for it.
Yeah.
And you have to have the enzyme present. But that's what basically our body's way, our cell's way of controlling what peptides get formed at any given time is basically goes so quickly when it's catalyzed. That allows it to sort of control things a little bit. And that's also why our body has a mechanism inside all the cells to break down peptide bonds as well. Seems counterintuitive. We have an enzyme whose job is to make the peptide bonds, but we also have an enzyme whose job is to break down the peptide bonds. But what that does is it kind of gives your proteins that are in your cells a finite lifespan, while also protecting your cells from foreign proteins. Because we don't really want our cells to keep around foreign proteins, because that's how our cells get hijacked in an infection, right?
Yeah.
So we have these enzymes called proteases whose job is to break down proteins. And they're always present in low concentrations, so that when protein is not being used anymore, even if our cell wanted it initially, it needs to be constantly replenishing those proteins because it's also constantly breaking them down.
Petition for a biochem class here.
Unfortunately, it won't do us any good because the biochem that you need for pre-med and most science majors need is an upper division class, and we're not allowed to. It will never transfer. So it's Upper divisions are not allowed. It depends on what school you go to. Most schools, you take organic chemistry your second year, so it's a 200 level class.
That is under.
No,
No,
upper division is 300 or 400.
yeah. So I'm still doing on my lower group.
So they just break it up into 1 and 200 level versus 3 and 400 level. We're allowed to offer 1 and 200 level, not 3 and 400.
No, this is referred to. Like a 5 second. And then I had them. This is my second year. No, it's not. I graduated next 2024. This is my second year.
Blowing your mind right now?
I have 2 years. You must have.
Unless you weren't here yet. From Sonoma, when did you graduate from the CHS? Okay, then yeah, was it a COVID year? Maybe that's why you're not remembering it as much.
No, but she did was nice. She did a light year. I did like a part-time year. So, okay, you would have done the light year when I was asleep. Yeah. Then you would have been here the next, and we took biology together. No, because I had my light year and
Okay, so you did your light year first.
third year.
So this is your 4th year.
But didn't you do January before biology? No, you're not seeing that.
And that's fairly common. This is why organic chemistry is not an upper division class, is because for chemistry majors and pre-meds that are going straight to a 4-year, it's pretty common for you to take gen chem and bio, sometimes even physics, all in your first year. Right. So if you tack biology on that as well, that would be a typical first year at a 4-year for a pre-med. You just spread it over 2 years so that you could work and not overwhelm yourself at the same time.
Yeah.
Which is frankly a better idea.
It was hard not to take 2 3/4 classes at the same time.
Yeah.
I didn't need a third one.
Yeah. I didn't take physics until my junior and senior year, my 3rd and 4th year.
I'm really glad just because that taught me how to take a science class in college.
Yeah. Physics is really good for that, and it lays the groundwork for a lot of the stuff we talk about later in chemistry. I didn't because I had AP credit for calculus. I jumped straight into calculus 2, which conflicted with physics. So I put physics on hold so I could take calc 2. I could have done those the other way around, but I'm glad I didn't, because since I took calc 2, and I was in there with all the math majors, but they're like, you realize you only need to take 2 more classes to be a math minor. So I added a math minor, just because I happened to take that class instead of physics my first year. But anyway, all right. So what would we make for each of these? What's our nucleophile and what's our leaving group? Don't worry about drawing mechanisms. I say that in show our work, but we get a tetrahedral intermediate. Then the chloride is better leaving group.
Wait,
I mean,
so the oxygen that's down there came with the oxygen that's on the arrow? Okay.
yes, thank you. That this is the case for college. Since we're learning this for the first time, let's color code it. right? So we replace the chloride with this entire acid group to make an acid anhydride.
Can we name it?
Yes,
Right. What?
we haven't done any practice with the anhydrides yet.
We did like one very funny things, but it's symmetrical.
Symmetrical, which makes things easier. And actually, I think we just leave the acid, and we instead of saying acid, we just say anhydride.
Okay, and we don't say like dye.
No, it's if it's symmetrical, you just say that. Because you're assuming it's symmetrical unless you're told otherwise.
Okay, so
And sometimes you will just see it written as propyl instead of propanoic,
okay.
especially if it's asymmetric. So let's say we were looking at that instead.
Yeah.
That would be either acetyl or ethanol. Acetyl propyl anhydride or acetic propanoic anhydride.
Okay.
They're both acids on either side, right? If you cut it here, that's propanoic acid. If you cut it here, that's acetic acid. So you just say both of them.
Fine.
Mhm.
It's purple.
This one?
Yeah.
Let's call it black, because that's the one that is new bond. The purple came from our starting material. Blue is our new material, so the orange line is the new bond between.
We try it.
Sorry, before I erase all of this, let me redraw that. Which side is favored in equilibrium? Sorry, this or this?
Wait. Yeah, chlorine is our most reactive, so it has to be our products.
Bingo.
So we're gonna say that our methyl group is our nucleophile.
Correct.
Why do you think drawn like that? Why is it? Oh, it's not a reaction. I thought I understood. So the methyl attacks the carbon.
It's process. It's not the methyl, it's having carbon, no, it's the oxygen.
Oh, okay.
It's the oxygen for the partial negative is, right? And then take up the pi bond to make room for it.
Yes.
So our intermediate looks. And if we're really showing all of our steps, we would have to show some proton transfers in here.
What happened to our colors?
Sometimes I do that and people look at me like why would you bother doing that? Sometimes it's really helpful. We're starting to bond again.
Yes. Okay. So yeah, how do you get rid of the OH? Yeah, but like, yeah.
So this is gonna be the trickiest part of these is. Are we under acidic conditions or basic conditions? Because there's gonna be some proton transfer steps in there too.
Right.
It's just where are the proton transfer steps and what are they doing? In this case, we're under acidic conditions, right?
Yeah.
So we actually wouldn't see this right away. And so before we actually have this step, we would do a proton transfer to protonate that to oxygen. Seen that before, right? But this is good review. This is by far the trickiest part about these mechanisms. Is before we can have this. We protonate that. So our first intermediate is just the protonated carbonyl. Right, because we can't have a negative charge floating around if we have or under acidic conditions. And then we still have this OH still there. Now we can have a methanol come in and attack. And kick the pi bond up.
How do you know that's not the metal? How do you know it's the OH in the
What do you mean?
like NaOH regarding like, oh, then mental.
Because this is methanol, right?
Yeah, well, if you could be over, you need the same exact thing as before.
So I'm drawing it this way because the oxygen is what's actually attacking the carbonyl.
Oh, okay, that makes sense.
So once we get here, now we have to do another proton transfer because we can't take off either of these leaving groups as hydroxide because we're in acidic conditions. So we would need another acid around. And if these are both the same, doesn't matter which oxygen you show leaving because they're identical. So just protonate one of them. Then if we wanted to, since we're doing proton transfer, we could deprotonate this oxygen at the same time. You know our final product, it's not going to have this oxygen on there. So we could say, okay, well. A generic base, something that can accept the proton.
Would we probably use water?
Yeah, water would work.
And then you kick off the water at top.
Water leaves. We reform the pi bonds. So final product. Well, almost final product. Because we do still have a protonated carbonyl now. So one last proton transfer step. Acid-base conditions, acidic conditions. Trying to not use the word base. Acidic conditions require you to show more steps because you can't have any negatives around. And so you need to make sure that you do your proton transfers in the right order so that you never have a negative sign. If it's basic conditions, you can never have a positive. So you might need to do a deprotonation step at some point. Like we would never have, if we're under basic conditions, it's not going to be the methanol that attacks. We'd have to start with deprotonation of methanol. Because then you're only making negative charges.
Yeah.
So you just have to watch out for it. And just remember that rule. Acidic conditions, you can only have positive charges. Basic conditions, you can only have negative charges. Both of them are fine with neutrals, obviously.
Yeah.
So then our final product here would be methyl acetate or methyl ethanoate. And which of these is going to be favored? Is it acid or an ester more safe?
To do the last step.
To do the last proton transfer? Yeah, just write it either the same way as this or just use water again. And actually, if we're doing this, if methanol or reactor, you might not actually have that much water on, so you can also use methanol as your base as well, propionate methanol. But either way, if you just use the water, I'm not going to second guess you. So Riley, you said that the reactants are favored. Why?
Because the OH is not like very reactive, but the O carbon double bond O is.
So we're really comparing this as a leaving group to this as a leaving group. It's hydroxide
So it's this,
relatively.
okay,
So this is one where we can really control it pretty easily based on the conditions. If you take carboxylic acid and you put it in pure alcohol, you're going to favor making the ester. If you take the ester and you put it in pure water, you're going to favor making the acid. It's all just a function of concentration. They're pretty much same strength as a base.
so because we put it in acidic.
This one, I would say that there's not one side that's favored necessarily. They're roughly equal, which makes these really easy to switch back and forth.
And what did we gain?
So it is a ester and esters. So we're naming it as the acid. So either acetic acid or ethanoic acid, right? Except, so acetic or ethanoic. So if we drop the ic acid and change it to 8. So it's acetate or ethanoate. And then we just say what's on the other side of the oxygen. Same word or two separate words?
Separate.
Separate words. So methyl ethanoate or methyl acetate. The nomenclature is not that bad when we get used to it. It's just another wrinkle because we've never had to deal with that.
The separation, like the wording is different.
Yeah.
And big.
Yeah.
I was gonna say in 2 years.
All right. Let's do the last one when we come back from break.
Oh.
Let's come back at 10 after.
Maybe I'll try to call that one. The same kind of almost boring. Guess we didn't pick up. No, this is the woman, I've already done the other 3 things that I've had to do. She emailed me and was like, oh, I need to know like what to say basically. So I was gonna email that, so at the bottom it was like, call me anytime at this number to let me know, like, or texting is good too. So I called, but should be done, should get back. So I texted, and then look, literally, this is just take my freaking text message. It's yeah, it's been 500. Look, I said hi, Lori. I called you yesterday, but I haven't heard back yet, so I figured I'd shoot you a text. This is where the end of confidence you emailed me about how I would like to be introduced at this relevant scholarship ceremony. Something like, quote, Bradley is an inspiring oral surgeon. She will be graduating from LTCC with her AA in liberal arts math and science this June for continuing her education at Webinar. Should be good. If you need more or less, please let me know. You are welcome to share any other information that I have shared in my application as well. Please let me know if you need anything else from me or would like to chat. Thank you. Just a little bit. So sorry for the it's not my office. May I call you this afternoon? If so, that's a good time. And I was like, oh, extra $300. Fortunately, I have work from now on. Like tomorrow. I am so like, thank you.
Wait a second. Yeah. And then he got hit right for arms, which is why it's balanced. And he caught another one off the side, on a balance. And he was just. Yeah, he had great his on base percentage, 1,000. Yeah, he got 2 hit by pitch, 2 hits. Okay. He got a single on a hard grounder, and he put one right out in between right and center, all the way to the fence, got a double. So he had a great game. He was just hurting the whole time. Yeah. This super funny. I just came to Dash's baseball game on Tuesday. And Dash had a pretty good game, but he was just a magnet for the baseball. He was just getting crushed. He started out his first play appearance, he bunted the ball into his own knee. And they just solidly bunted it, and it was standing in such a way that it put it right off the inside of his knee. Went down. And he has a bunch of bruises and he's very sore. But and then the next pitch he got hit by the pitch. So he hit himself and then got hit by the pitch. And then his next at bat, he got hit by the pitch by a different pitcher.
Great.
And then he started taking foul tips because they were getting close to hitting, and he's the catcher. So he was catching, he got one right off his forehead.
Awesome.
And then another one on his forearm and another one on his other leg. He was just in tears by the end of it.
Oh my God, that sounds so good.
It's the life of a catcher.
Because yesterday, one of my girls at the end of our class, she like sat down, she, what's your last name? And I immediately in my head am going, shit, who did my mom fire? And I go under Poplar, and she goes, do you know who Vale is? And I was like, because I'm trying to think about who, like, in Ariel do I know with this name? I'm like, I don't think I do. She's like, oh, I was talking to my friends, and I was like, oh, I have Ariel name. And she was like, with writing under Poplar. And so I did you know what your last name was? And I was like, who was this? And she was like, Valence, Vale. And I was like, oh, now I know that.
I always call her Valence, but her friends call her Vale.
Yeah. It makes sense as a nickname, but I had just never heard it before, so I didn't connect those dots.
Yeah. No, Valence loves knowing everybody.
Mm.
She also flew everybody. The kindness club came to visit on campus here, and it was Caroline and Carl
Okay.
that met with them.
Yeah.
And so when they got back, the kindness club was talking about they met these 2 professors that teach biology. And Valence goes, "Oh, you mean Carl and Caroline?" That's one of her favorite things. Exactly. Yeah. All right. I need to make a quick phone call.
Okay.
In 2 minutes, then we'll come back.
So, yo. That's right. So, no. What's better? Yeah, this one is great.
All right. So same functional groups and leading group as first one, just different nucleophile. If we have ammonia as our nucleophile, is that acidic or basic conditions?
I mean, it has 3 hydrogens, so I feel like it might.
It has 3 hydrogens, but ammonia in water is a weak base, not an acid. So this is going to be under basic conditions. Amines get protonated really easily under acidic conditions. So the fact that if it was acidic conditions, it would be NH4 plus
Okay.
ammonium, which is not a nucleophile because it doesn't have a lone pair.
Yeah.
So the fact that it's ammonia in its neutral tells us we are under basic conditions.
So the lone pair attached.
Lone pair attacks first. It's okay, we're going to erase this real quick anyway because we committed a cardinal sin. We made a positive charge, but we're under basic conditions. So first step before it attacks actually has to be to deprotonate the nitrogen. Not really a cardinal sin, more like a common, not all that important mistake. So we need something around probably another ammonia to grab one of those to make NH2 minus, which then can come in and attach.
Okay.
Then what's our next step?
Make the. Oh,
Okay.
no, it's sleeps.
Because we don't need to protonate it first because we're under basic conditions.
Okay.
So we can make our leading group lead without protonating it because that makes us negative charge, which is okay.
That's
Yeah. Sure. Let's figure out which side is favored by equilibrium first. That's the easy one. Yeah. Amides are the most stable thing we can make, the most stable acid derivative. And acid chlorides at least.
Yeah.
So not only is this gonna heavily favor this is actually probably gonna be so exothermic that it might catch on fire. We actually try to do it. We get really good yield though.
Yeah, that's true.
So then naming this, if it was the acid, it would be two methyl propanoic acid, right? So we name it as the acid. Cut that off. Say amine. So 2-methyl propanamide. Just so that you've seen this, I think you all could figure this out yourself. If this was a methyl attached here, now we have 2 methyls, right?
Yeah. So we would say N methyl at the beginning.
Right. 2, N dimethyl.
Okay.
So we can mix and match.
The amino. The running space.
Correct.
Okay.
The amides, because they have that in locants that allows us to specify their attached to nitrogen. The reason we don't do that with the esters is because we don't have,
I like the way to
we
say.
don't say, oh, in theory you could, if I was redesigning back from scratch, that's what I would do. So you could say, oh, ethyl,
Right.
but that's not what they did when they made it. However, these are common enough that we see N all the time. And we can combine them like this. You can have a number and an N for the dimethyl.
Hard. I know that. I guess the prescribed word is now no longer.
Oh, the one on Pioneer today? Oh, good. That's right by my house.
Fantastic.
Yeah.
Well, I drove by it today and I was like, it's a lot of smoke. But I was like, I saw a bunch of people and all the signs were up. And I was like, okay, it's fine.
I saw the hoses.
Yeah.
When I was on there. They hadn't started yet when I left the house, but fun.
Yeah, exciting things to talk about.
It would have to jump. It's not windy days. And it would either have to go through about 100 houses to get to mine or
Jump.
go all the way to the airport meadow.
Okay.
Because we live at the bottom of that hill
Okay. Yeah.
on the airport side, so we're really close to the meadow, but it would have to get there first.
Yeah. I like, wait, is it like that weird road that like when you're driving from like our place this way, there's that before the airport, like that goes down?
No, so I live off of Pioneer.
Oh.
So when you take Pioneer, there's that frontage road, that section as a frontage road. We live at the bottom of that hill, off of Washouwen. So we're on the Pioneer side of the airport, but right on that meadow.
I feel like I definitely would let it gate.
They usually don't have an issue, especially this early in the season.
Yeah.
With them getting too out of control. All right, so this is just showing why we have to be careful with our proton transfer steps. Because if you look at at the energy difference between if we protonate it first or second. So if we're under acidic conditions and we protonate and we don't protonate this first, we make something that looks like this. We've got the plus and the minus on the same molecule. It's way uphill in energy. If we're under acidic conditions and we protonate the oxygen first, now we only have a positive charge and we're under acidic conditions. That's a much smaller activation energy to have our nucleophile. So you could still get to the right product and get those steps mixed up. But if we're trying to be careful about what those steps actually look like,
Yeah.
we have to do it properly. All right, so here's your summary slide. In acidic conditions, you're not going to make a negative charge. Under basic conditions, you're not going to make a positive charge. If it's at all possible to avoid it. Things that. So for that last one, where we said, oh, we had to deprotonate the ammonia before it could attack. Ammonia is not a strong base. So even if we're under basic conditions, we could still make that intermediate that looked like this to some extent. That's a possibility even under basic conditions because this isn't a strong acid. But just to have good habits and to give ourselves a really good general rule, think about the charges. If there's any possible way to avoid a positive charge under basic conditions, do it. If there's any possible way to avoid a negative charge under acidic conditions, do it. All right, so just as a general rule, there are 3 times when we can have proton transfer. These are our the two gray steps are the 2 steps that need to happen for a nucleophilic acyl substitution. You have to have a nucleophile attack and you have to have a leaving group lead. But anywhere in there, before the nucleophilic attack, between nucleophilic and the leaving group, or after the leaving group leaves, you can have a proton transfer. Nothing we haven't seen before, but this just kind of puts it in a really visual way to think about it. And so under acidic conditions, we have a positive charge and our intermediate has a positive charge. Under basic conditions, we have a negative charge on reactants and negative charge on our intermediate. So let's do a practice. I'll give you a head start for you two to work together on that. Okay. So part of it in this case is figuring out what is the product we're trying to make. In this case, we don't really have, if we protonated this oxygen and lost the water, we get something that couldn't really make a carbon oxygen double bond, right? So we're going to try and kick off the methanol.
Yeah.
The key is that it has to be methanol. We can't have it leave as a leaving group like this.
Right.
Because that would be a strong base. So we need something that can accept that. So just another H plus from whatever acid is around. And then this is another case where we know we're going to lose that proton at some point too, right? So we might as well do, if we have two separate proton transfers happening with the same molecule, we might as well show them at the same time. So just something, probably another ethanol molecule. But if you wanted to draw water, you could, or if you wanted to just draw base, you could. And so now our intermediate looks like no color coding. So now we're ready for our leaving group to leave and for us to make our new pi bond. And so we can show those bonds breaking and forming a new pi bond, which gives us at which I'm drawing the ethyl out instead of just writing ET, but that is almost our product. What's the last thing we have to do? Proton transfer. So another random base around. And then we're there. So if I was going to make a general rule for acidic conditions, you're pretty much going to have proton transfer every step of the way. You have to have a proton transfer before you can attack carbonyl. You have to have at least one proton transfer, if not two, in the intermediate. And then you have to have a proton transfer at the end as well. Bases, there's might be some proton transfers, but they're more rare. How do we feel about this? Good. Because we really covered more than three chapters, but three basic themes this quarter, right? Aromatics, the class 2 carbonyls, and now the acyl derivatives. The class 2 carbonyls all basically have the same mechanism. It's always that addition reaction. You break the pi bond and you add something to both sides. Our acyl derivatives are pretty much all going to be the same reaction as well. It's going to be some form of this reaction. And then we have the aromatic reactions where there was definitely a theme where we spent the most time on about two mechanisms there. And so if I was guessing which three mechanisms would be likely to show up on the midterm, one's going to look like this. I might mix up acid and base conditions and exactly what the products and reactants are, but I'll just about guarantee you it's going to be one of these. And you're going to have a nucleophilic addition reaction of some sort. The only way I could really make that tricky is if it was a Wittig reaction, because that one looked a little bit different, but it was the same net result for the most part, right? And then there was really only three mechanisms that we looked at back for aromatics too. And they all look kind of similar, which is, do we have that sigma complex, or do we have that elimination addition reaction that has similar but opposite charges intermediate, right? All right, there's more practice for these. These are the same reactions we already did. And we actually already started doing this. We got ahead of ourselves because we asked the right questions, which is perfect. So we already kind of did all of these, but if you wanted, and then we did not do with the idea of make sure you keep the right charges on your intermediate. So you might go back and look at what we wrote for that and make sure we did it right. All right, so that leads us to our other reaction. If we can always go downhill with these acid derivatives, right? If we can make an acid chloride, we can make any of the other acid derivatives.
Acid. Yeah.
Right, so if we can get to this, we can make any of the other acid derivatives we want. So we just need a reaction to do that. And it turns out, if we use, this is a molecule we've seen before, thionyl chloride showed up back last quarter sometime. I'm trying to remember exactly what the mechanism was, where it showed up. It's going to work pretty similarly here. But this, it's not a true and I would actually probably show this one the same way as our last nucleophilic attack. We draw the lone pair of attack from here instead of drawing the pi bond over there.
If it's the bond attached on a reagent.
That's the net result of it. You can kind of, the thing about electrons is they're all indistinguishable from each other, so it's hard to say if it's those electrons attacking the sulfur, or if it's these electrons attacking the sulfur, and these ones just come up to be a lone pair. That's the same net result either way, it's just drawn a little differently. But the net result is that we switch the pi bond between these two. Okay, so the pi bond was to the top oxygen. When the sulfur comes in, the pi bond switches to being the bottom oxygen. So what's different about this mechanism compared to the last one is that this one doesn't have a tetrahedral intermediate on that part. We don't fully break the pi bond like we did on the last slide. We just moved it. Basically, this all comes down to the fact that sulfur oxygen bonds are more stable than sulfur chloride bonds. Or you can think of it as chloride as a better leaving group. So we're basically going to replace the chlorines that are attached to the sulfur with oxygens. So now we wind up making this you could also consider this an acid derivative, because it's still a carbonyl attached to something that's a really good leaving group. It's just a more specific one that we don't see very often. It's so unstable that we don't really see it show up very often. So we made this leaving group. And then it's the exact same mechanism we already did. We just have chloride acting as our nucleophile in this sulfur oxygen group acting as our leaving group. So nucleophile attacks, we make a tetrahedral intermediate, we kick off the leaving group and reform the pi bonds. And then this molecule does a little bit of rearranging on its own to make SO2 and chloride. We really don't care about that very much though. It's helpful because SO2 is a gas, so we can drive this to completion with Le Chatelier's. But it doesn't really matter. The net result of this whole process is you can take a carboxylic acid and turn it into an acid chloride. And now we can get back to any of our other acid derivatives that we want.
Yeah.
All right, so these other acid derivative reactions, or converting back and forth between them, have different names, but they're all the same thing. If you take an acid chloride and you put it with water, you get an acid, and they call that hydrolysis.
So we like preparing acid chlorides via via hydrolysis,
No, these are all once you made the acid chloride.
like this could be a different step too.
This is once you make the acid chloride, this is how you get to all the other functional groups. Because if you look here, we've got acid, ester, and amide, substituted amide. We have we make an acid anhydride this way. So this is, just to reiterate, this is the way we make the acid chloride. And once we make it, we can use it to make all of the other acid derivatives. And that's what this slide is. Right. So let's do a fun applied example. This is salicylic acid. Naturally found in willow bark. A common traditional remedy for headaches is to make a willow bark tea. If you expose this molecule to acetic anhydride, so acetic anhydride is going to look like this, right? We get acetyl salicylic acid, which is better known as aspirin. What is that reaction going to look like? What is the product going to look like? If we let this molecule react with this molecule, there's two functional groups here. Which one is going to be more likely what? It's but the product that we would get. So if we did that, if we had this come in after the nucleophile here, and this kicks off after a step, I'm skipping all of the proton transfers. We would still make another anhydride, right? And it would be, we get that. So we go from one anhydride to another anhydride. So no net gain in stability there that way, right? What do we get if the other functional group attacks? If the alcohol attacks, that's not an anhydride anymore. We wind up with an alcohol being attached here. So we get something that's going to look like what functional group is that? Ester. So we went from an acid anhydride to an ester, and we left this one home. Is that downhill energy? Acid anhydride more reactive than an ester, or about the same, or less reactive?
Less. Oh, wait, no.
The anhydride is more reactive. So this is what we see. And you actually can get that to happen just with vinegar and salicylic acid. So if you took vinegar and salicylic acid and let them react, it's going to be a slow reaction. But you can actually make aspirin. You have much better yield if you use acetic anhydride, which is what we do commercially and in lab. If you remember making aspirin in, this is the reaction. This is the reaction we did.
Yeah.
And now you understand the reaction more.
Yeah.
So maybe this would be a good, this is not a particularly tricky lab. It's one of the reasons why I would start with this one when you're first learning how to do OChem. because it gives really good yields and nice fluffy crystals that are really easy to recrystallize. So maybe if we have a spare lab at some point, we'll do that one since Taylor hasn't done it yet. You're not allowed.
You're the one for each, right? Yeah. Yeah, that's one for eight. It's not just one to.
Not only can you not eat it, I won't even let you take it home to remove the temptation. All right. Last thing that might show up on our test is if we want to reduce this applies to any of our acid derivatives, acid chlorides, esters, acid anhydrides, etc. They're all fairly offsets, right? If we want to reduce them, we just use either lithium aluminum hydride. If we want to turn it all the way to a primary alcohol, or we use Grignard reagent if we want to turn it to a tertiary alcohol. We've seen these reactions before, right? Just not with acid chlorides. It turns out it's the exact same reaction for any of the acid derivatives. The only one where you might not get great yield would be the amides because they're already so stable. If you try to reduce an amide this way, I believe you just get the amide. You can't take the nitrogen off. Not the amide, you get the, I don't remember what that functional group is called, where you have an OH. But point remains, this applies to any of them. The new thing we're going to add in the last minute is that if you, and the reason we're going back to this because it's really important sometimes. You'll notice that on the previous slide, we can make a primary alcohol or we can make a tertiary alcohol.
Yeah.
But what if we wanted to make a secondary alcohol? We don't have a way of stopping this reaction halfway through. When we first learned Grignard reagents, we talked about that a little bit, right?
Yeah.
We don't have a way of doing the reaction halfway with the Grignard reagent. So if we want to partially reduce something, you can either use lithium trialkoxy aluminum hydride. It's like lithium aluminum hydride, except we only have one hydride to give. We only have one hydride to give, we actually can use this again. The problem with lithium aluminum hydride is it's strong enough to reduce the acid derivatives, but it has too many hydrides to give and we can't stop it partway. Similarly, if we want to do a partial reduction where we add a carbon in order to get us to a ketone, which then we can finish reducing to a secondary alcohol, we have to use what's called a Gilman reagent. And so a Gilman reagent looks just like a Grignard reagent, except instead of magnesium, it uses copper. Right, so if you have an R group attached to a copper, that will let you go, it'll let you add one carbon, but not two. So this gives us the flexibility to do our reduction in 2 steps. Instead of the old school way, we went and had to do all of our reduction at once. So we couldn't change what our nucleophile was.
Right.
And same for this one. So if you want to add the same thing twice, Grignard reagents or lithium aluminum hydride are fine. But if you want to add 2 different nucleophiles to do your reduction, it has to be with these steps, with one of these steps. Okay. And that applies to if I wanted to add a methyl group and then an ethyl group, I could do that. I would do the methyl group this way first, and then I would use an ethyl Grignard reagent. Then Grignard ketone works just fine. Or if I wanted to add one hydride and then follow it up with a methyl group, I can use this and then follow it up with a Grignard reagent once we get to the alcohol. Right, so this allows us to mix and match in a way that just the Grignard reagents and just lithium aluminum hydride don't. Okay, so that's why they're important and why I'm trying to cram them in here in the last second, is because these are important reactions for synthesis. We ran into that with our synthesis project, right?
Yeah.
How do I reduce it by one step but not two? This is how. Not that one. This is how. Okay, so those are the last reactions. There's some practice.
Or practice test.
And your practice test will come out today too. These are really good for the reduction reactions. Because you have lithium aluminum hydride, or you have Grignard reagents, or you have add one hydride and then a Grignard. Or add one ethyl group and then a hydride. Etc.
Yeah.
All right. Good job. Later today, I'll send out the practice test. And we'll go over it on Tuesday. I'm around via email tomorrow. I'm in meetings all day, but I should be around over the weekend, less so. But I'm also here on Monday. If you wanted to come in and ask questions on Monday.
So, or you guys are together. Well, when are you gonna have this